Chapter 34 Standard Enthalpy Change of Reactions. In this chapter, we are going to learn the definitions of standard enthalpy changes of combustion, standard enthalpy change of neutralization, and standard enthalpy change of formation. After that, you are going to learn some experimental method to determine the enthalpy change using simple calorimetric methods. Now, please turn to the next page. Let's talk about standard. What is the meaning of standard? Okay? Standard enthalpy change. In Chapter 33, we have talked about enthalpy change. Do you remember what is it? Let's have a revision. Enthalpy change is the heat change at, do you remember? At constant volume or constant pressure? It should be constant pressure, not constant volume. Bear in mind, okay? Now, standard. Okay, what is the meaning of standard? Let's talk about burning of fuels is an exothermic reaction. For example, burning of methane, burning of petrol, burning of diesel oil, etc. is an exothermic reaction. In order to compare the enthalpy changes, okay, we have to fix the conditions. That means we are compare the enthalpy changes when different fuels are burned. In order to compare enthalpy changes fairly, to have a fair comparison, it is necessary to specify a set of conditions under which enthalpy changes are measured. Okay, we have to fix good conditions in comparison. So, what is the meaning of standard conditions? The standard conditions adopted for these measurements are, the first one, pressure. If we are talking about pressure, we are talking about 1 atmosphere. And now, for physics students, you should be very familiar with this type of unit for pressure. There are many units for pressure. ATM is commonly used, 1 ATM. Another unit very commonly used is an SI unit, is Newton per meter square. A lot, Pascal, like Torr, etc. Okay, there are a lot. Try to remember these two first. The unit for pressure is ATM, or Newton per meter square. We are living in 1 ATM environment, okay? 1 ATM is equal to 101.325 Newton per meter square. If you go up a hill, a very, very, very tall hill, maybe the pressure is lower than 1. Maybe 0.8 ATM, like if you go to Saigon, okay? Pressure, the air pressure is low. But if you dive into the water, the pressure is higher than 1 ATM. ATM is a commonly used unit for pressure. Another commonly used SI unit for pressure is Newton per meter square. 1 ATM stands for 101.325 Newton per meter square. Next, if we are talking about temperature, the temperature must be 25 degrees Celsius or 298 Kelvin. Again, I must emphasize, for physics students, you know that pressure may express in Kelvin unit. What is the meaning of Kelvin? Kelvin temperature is equal to Celsius temperature plus 273. That means 25 degrees Celsius is equal to 25 plus 273 Kelvin, therefore 298 Kelvin. Or today is 20 degrees Celsius, 20 degree. If we need to change the unit to Kelvin, it is equal to 273 plus 20, which is 293 Kelvin. Understand the interconversion between these two units, degrees Celsius and Kelvin. In calculation, we often need temperature expressed in Kelvin. Concentration. A concentration of 1 m if the substance is present in solution. 1 m, 298 Kelvin. One more. The substance involved are in their stable standards. Stable standard. In their stable standard. Now, I give you an example. What is the meaning of stable standard state? Let's use carbon as an example. Now, in book 1, you know that there are more than 2 forms of carbon. One is in graphite, and another one is diamond, C60, C70, nanotube, etc. Okay. Stable form of carbon at 25 degrees Celsius and 1 atm is graphite. So if we need to use carbon, then we are talking about this form, graphite. Another example is phosphorus. Stable form is red phosphorus, not white phosphorus. In other words, phosphorus has 2 forms. One is red phosphorus, more stable form, and another one is white phosphorus, not stable. It will ignite by itself, burn with a pale green flame. Oxygen, not ozone, okay? Ozone is O3, not ozone, are chosen as the stable states for carbon, phosphorus, and oxygen respectively. Now, I will repeat this point by using equation, okay? The enthalpy change of reaction measured under the standard conditions is regarded as standard enthalpy change of reaction. Standard enthalpy change of reaction, okay? Next, let's talk about the thermochemical equation. If the enthalpy change is measured under standard condition, the delta H will have a phi. This is called phi. This symbol phi denotes that the reaction takes place under standard conditions. Without phi, that means the reaction takes place under other conditions, not standard conditions. Besides, the unit are kilojoule per mole, not joule in chemistry, okay? Kilojoule per mole. Let's use some example to understand what is the meaning of standard conditions. Let's talk about this reaction. Carbon solid react with oxygen gas to form carbon dioxide. Now, first of all, in thermochemical equation, states are very, very, very important. Don't miss, you cannot miss the state, okay? For carbon, the stable form at standard states is graphite, so sometimes it is written in this way. Instead of writing solid, we will put graphite inside the bracket. Oxygen state at room temperature, that means 25 degrees Celsius and 1 atm is gas. Carbon dioxide under standard condition is a gas. Okay. Next, please check, is that balanced? Yes. Okay. And then after the equation, we will write down delta H5, which is negative 393.5 kilojoule per mole. Negative, do you remember what is the meaning of negative? Negative means exothermic. Do you remember? Exothermic. That means 393.5 kilojoule of heat is released. Okay, when 1 mole, we're talking about mole, 1 mole of carbon atoms reacts with 1 mole of oxygen to form 1 mole of carbon dioxide under standard conditions. You must mention under standard conditions, because if you look at this symbol, there is a phi symbol. Can you see that? There is a phi. So in your expression, in your interpretation, you must tell me under standard conditions. Besides, we must mention the number of mole involved. Now, let's repeat. But this is a thermochemical equation. States are very important. And then by looking at this equation, what do we know? That is, when 1 mole of carbon graphite reacts with 1 mole of oxygen to form 1 mole of carbon dioxide, 393.5 kilojoule of heat is released under standard conditions. Now, please repeat what I have said, okay? Now, actually, we are talking about this definition, standard enthalpy change of reaction. Is the enthalpy change when the number of moles of reactants represented by the thermochemical equation react completely under standard conditions. Use a highlight pen, highlight under standard conditions, because we are talking about standard enthalpy change. Underline this first, and then use another highlight pen, another color, to highlight when the number of moles. We must specify clearly the number of moles of reactants reacted. Okay? Now I will emphasize about this point later. Now, let's talk about the states. Why states are very, very, very important. Let's compare these two equations. H2 gas reacts with half O2 gas to form water, which is in gaseous state. H2 gas reacts with oxygen, half oxygen, to form H2O liquid. They have different enthalpy change. If we are talking about the formations of steam, it is negative 241.8 kilojoule per mole. If we are talking about the formations of water, delta H is equal to negative 285.8 kilojoule per mole. Now, what does this means? Start from the first one. When 1 mole of H2 reacts with half moles of O2 to form 1 mole of H2O steam, 241.8 kilojoule of heat is released. It is not necessary to mention under standard conditions because there is no phi in the superscript. Now let's look at another one. When 1 mole of H2 gas reacts with half moles of O2 gas to form 1 mole of H2O liquid. 285.8 kilojoule of heat is released. Again, no need to mention, understand the conditions. They are different. Use a highlight pen again, highlight gas, liquid. They have different delta H. Of course, they are different because look at this paragraph. If the product of the reaction is steam, H2O gas, the heat released is 241.8 kilojoule per mole. If the product is liquid water, the heat released is 285.8 kilojoule per mole. The difference is 44 kilojoule, okay? It is the amount of heat released when, underline, steam condenses to liquid. Now, you know that when steam condenses to liquid, do you remember? Is it an exothermic or endothermic process? You may consider from liquid to steam. Liquid to steam is endothermic. Therefore, steam condenses to liquid is exothermic. So 44 kilojoule per mole of energy is released. Do you understand? From steam, gas condensed to liquid water. Now, I would like to relate these two equations together on an enthalpy level diagram. Here, for the first one, this is the first one. This is the first equation. H2 reacts with half moles of O2 gas to form H2O gas. It is an exothermic reaction. Exothermic means pointing downwards. Okay? So look at the enthalpy level diagram. Bear in mind, you are required to label the axis. The y-axis is enthalpy. X-axis is reaction pathway. Okay? If you miss the x-axis, it doesn't matter because x-axis is meaningless. H2O gas reacts with half mole of O2. Half mole of O2. Okay? And then how much energy is released, which is 241.8. So pointing downward, the amount of energy released is negative 241.8 kilojoule. Pay attention about the state, which is the gas, formations of steam. Now, let's look at the second equation. It is the formations of H2 gas from half O2 gas to form 1 mole of H2O liquid. Same starting material, therefore the reactants are the same with the same enthalpy, with the same height. I would like to draw two diagrams together, okay? Instead of two, I combine these two together. Same height, but now more energy is released. So here is H2O liquid, and the amount of heat released is negative 285.8 kilojoule per mole. Do you understand? Now, here, from gas to H2O liquid is equal to negative 44 kilojoule per mole. Okay, subtract these two data together, then you can work out negative 44 kilojoule per mole. In other words, when 1 mole of H2O steam at gas state condensed to 1 mole of H2O liquid, 44 kilojoule of heat is released. Do you understand? In other words, by using this page, states, physical states, must be specified. So please highlight this sentence. Must be specified in the thermochemical equation. If you miss the state, you got no marks. Bear in mind, okay? Next, how about the direction? If we reverse a chemical equation, the sign of delta H is reversed. Now, what does it mean? Here, there is an example. H2O gas reacts with half mole of O2 gas to form H2O liquid. When 1 mole of H2O gas reacts with half moles of O2 gas to form 1 mole of H2O liquid, 285.8 kilojoule of heat is released. Okay, is released. That means by using the enthalpy level diagram, here is the H2 gas and half mole of O2 to form H2O liquid. Because energy is released, delta H is negative, so use the red arrow. Do you understand? Now, if you reverse the chemical equation, that means from H2O liquid, change it back to H2, 1 mole and half moles of O2, the delta H will have a positive sign and of the same amount, same value, positive 285.8 kilojoule per mole. Obviously, if we reverse the chemical equation, that means it is represented by this green arrow. Therefore, the arrow now is pointing upward. Therefore, it will have a positive sign of the same value, positive 285.8 kilojoule per mole. Now, by using this example, I must emphasize, in writing an equation, okay, the direction, that means which are the reactants and which one is the product, are very important. Don't reverse the equation. If you reverse the equation, the delta H will be different. Do you understand? How about if I multiply the equation by a number? Now, compare these two equations. 1 mole of calcium solid reacts with half mole of O2 to form 1 mole of CaO solid. Delta H is negative 635 kilojoule. What does it mean? It means that when 1 mole of calcium solid reacts with half moles of O2 to form 1 mole of calcium oxide solid, 635 kilojoule of heat is released. Is that right? If I multiply the equation by 2, change it to this form, 2, 1, and 2. That means now we have 2 mole of calcium solid react with 1 mole of O2 gas to form 2 mole of calcium oxide solid. The delta H is changed, is increased by double the amount, because now we are talking about 2 moles, okay? 2 times negative 635 kilojoule, which is negative 1,270 kilojoule. So, if you multiply the equation or divide the equation by the same factor, then delta H must also be multiplied or divided by the same factor. Do you understand? Here, please underline this sentence. Delta H must be multiplied or divided by the same factor. Okay, now let's try class practice 34.1. The standard enthalpy change of the following reaction is negative. Negative means released, okay? Heat is released. 1,371 kilojoule per mole, represented by this equation. Now, what does it mean? It means that Now let's repeat. When 1 mole of ethanol liquid reacts with 3 moles of oxygen to form 2 moles of carbon dioxide and 3 moles of water liquid, 1,371 kilojoule of heat is released under standard conditions. Do you understand? So, how much heat in kilojoule is released in each of the following cases? When 2 moles of ethanol and 6 moles of oxygen are used. By looking at this equation, we are talking about 1 mole react with 3 mole. Now it asks about when 2 moles of ethanol and 6 moles of oxygen. What should be the delta H? Okay, how? It is equal to 2 times 1,371. Do you understand? Which is equal to negative 2,742 units. Is very important, kilojoule. Do you understand? How about when 11.5 grams of ethanol is used? First of all, you must work out the number of moles of ethanol. Number of mole of ethanol is equal to the mass of ethanol over molar mass of ethanol. Use your calculator. The number of moles of ethanol burnt is 0.374 mole. So the amount delta H in this situation, that means case B, is equal to negative 1,371 times 0.274. It is equal to something wrong. It should be 16. .25 mole, sorry, 0.25 mole. Negative 342.75 unit is kilojoule. Do you understand? Now, how about when 1 mole of carbon dioxide forms? Look at the equation. It describes about when 2 moles of carbon dioxide. Now it asks about when 1 mole of carbon dioxide forms. So can you tell me what is the delta H? Very simple. It is equal to over 2, okay, which is 685.5 kilojoule. Is there any problem?